All right, let's look at practice number 2. Hopefully you read that little bit about hypothesis testing for two independent groups. That's where we're going to start. And you see those two formulas. So it's really, of course, the test statistic that changes. How do we calculate the test statistic from one style question to another? And those two equations, one with the z-score, the other with the t-score, those are pretty intimidating, right? Well, we're going to walk through a couple questions. Hopefully, it'll be less intimidating after we get done. So let's go ahead. I'll read practice problem number 2. It is speculated that teenagers sleep more than adults on average. Okay, so we're going back to that scenario. To study this, a sample of 16 teens had a mean of 8.9 hours slept per night with a sample standard deviation of 1.2 hours. A sample of 12 adults had a mean of 6.9 hours per night with the sample standard deviation of 0.6 hours. These populations are normally distributed. Okay, so that allows us to have sample sizes less than 30. So we need to be clear that they are normally distributed already. All right, then with a significance level of alpha equals 0.05, is there enough evidence that teenagers sleep more than adults on average? Okay, well, we might have some thoughts about that just from our own experience. Let's see what the numbers tell us. So to begin, and you see this here on the screen, we need to decide which group we call by which number. So we need a group 1 and a group 2 because we need to be consistent as we calculate our z-score and even for the null and alternative hypotheses. So I'm going to say group 1 is the teens, group 2 is the adults. Why is that? Really, the only reason is they mention the teens first and they give the data for the teens first in the problem. So I said, let's make group 1 the teens, let's make group 2 the adults. Then we know we can be consistent. Okay, so what does that mean for the null and alternative hypotheses? Let me show you the null hypothesis and just focus here on the left. So back when we had just a one sample in chapter 9, we just had one group. So all we had was mu, and we said it was equal to a number, right? And that number was told to us in the problem. But that's not the case here. We're comparing the two groups. We're not looking at, one group versus this known larger population. We're saying this group versus this group. So what are we going to do? We are going to assume that the average number of hours between the two groups is the same. That's the null. There's no difference between them. Teens, adults, doesn't matter. We assume that they average the same number of hours of sleep. And we need a lot of evidence to convince us that no, actually one of them gets more sleep than the other. Okay. So an easy way to represent that would be to say H0, our null hypothesis, mu1 equals mu2. The average for the teens equals the average for the adults. Okay. Ignore what's over here just for the moment. So what would be the alternative hypothesis here? And we got to be really careful about the way that it was stated in the question. Is there enough evidence that teenagers sleep more than adults? Well, if group 1 is the teens, then we're going to put a greater than, right? The teens sleep more on average than the adults. This is bigger than that. Okay. So there's no numbers here at all, right? So what do I have over here on the right side? Okay, this makes perfect sense. It is perfectly acceptable to write your null and alternative hypotheses this way. There's no confusion there. However, the conventional way to write this that everybody has agreed upon in the statistics community is to write it this way, to put them both on the same side. So this first one, it's like we're subtracting mu2. So mu1 minus mu2 equals 0. And same thing here, subtracting mu2. Mu1 minus mu2 is greater than 0. Now, we'll see the reason. It's really this first one. We really like that, and that's to be revealed in step 2 right now. So this is really the way we want to showcase our null and alternative, although people sometimes do that. What is step 2? Step 2 is the big one, right? The test statistic. So I'm going to go ahead and pull this up off the screen because this is going to take a little bit of work. We want to identify all of the different parts for the two groups, and they tell us all those things, of course. So let's see, what is the average for the teens? It was 8.9, right? 8.9. Okay. They told us the sample standard deviation for the teens, right? 1.2. And how many teens were in that sample? 16. So the sample size for the teens, okay. Then we move to group 2, the adults. What was the average for the adults? 6.9, right? They give us the sample standard deviation for the adults, 0.6. And the sample size for the adults, it was 12. It was a little bit less. It turns out that is no problem at all. They don't have to be the same sample size. Okay. So now we can look, and at this point we got to choose which test statistic formula we're going to use above in the lecture. And well, we're going to choose the one that has the sample standard deviations, right? That's the t-score. So I'm just going to go ahead and show you the finish there. So we know it's a t-score because they give us S, sample standard deviation. So we take x bar 1 minus x bar 2. Now here's something interesting. Minus 0. In the formula, it says mu1 minus mu2 right here. So how am I able to just put a 0? Hey, didn't we assume mu1 minus mu2 equals 0? We're assuming they're the same, so that's gonna be a 0. Oh, okay. All right, so here's the difference in the data we collected, but we assume the difference is 0. Divided by giant square root s1 squared over n1 plus s2 squared over n2, 1.2 squared over 16 plus 0.6 squared over 12 from those four right there. If you would like to know why this is the denominator, here's kind of the thinking really for all of it. So we're always thinking the difference between the groups, right? So what's the difference between the groups? We're assuming the difference is nothing, right? So then here we look at, instead of originally back in the one sample, we just had x bar. Well, now we want the difference of the x bars. Back in the one sample, we just had mu here. Now we want the difference of the mu's. Turns out to be 0. So you might think in the denominator, we want like the difference of the original denominators. Well, it turns out, no, we don't want to take the difference of the standard deviations. We actually want to add the standard deviations, because standard deviation is like kind of got some error that it's factoring in. So we don't want to subtract the error. We actually want to add the error because we're more uncertain, if that makes sense. Anyway, this is our formula. Be really careful plugging all that in. You should get this result. I rounded that to 2 decimal places, 5.77. That is our test statistic. We've got step number 2. Okay. Step number 3. You may remember is calculating the p-value. All right. So I'm going to set it up. Step 3, the p-value equals the probability. Now it's a t, right? Capital T. Use our t calculator in StatCrunch. 5.77, a key moment. Do we pick greater than or less than here? Okay, remember it always matches the alternative hypothesis, which was a greater than. Another way to remember greater than, and this even works in the case where you get a not equal, if your test statistic is positive, you always pick a greater than. If your test statistic is negative, you pick a less than. And that just goes back to the normal distribution, that things on the left side are negative, things on the right side are positive, and we always want to be beyond. Okay, anyway. Some of you might have picked up on that already. So we want to look at probability that t is greater than 5.77. Okay, when you go into your StatCrunch calculator, it's going to ask for the degrees of freedom, right? Well, what do? I mean, we had two different groups. Let me pull back that previous sheet. We had two groups with two different sample sizes. The degrees of freedom is always one smaller, right? So do we pick 15 or do we pick 11? You always use the smaller sample size. And again, the thinking is the smaller sample limits your information. So you can't say you've got enough information up to 16 when you only had up to 12 here. So you have to always pick the less reliable source for the whole thing. It's like you're only as strong as your weakest link sort of thinking. All right, so we're going to use that 12, obviously different degrees of freedom. We take one off. So we take 11 degrees of freedom here. So take the smaller sample size. Put that all in, you should get 0.00006 as your p-value. Okay, moving on to step 4. We now compare the p-value with the significance level. Here alpha is 0.05. Well, alpha is most definitely the bigger one. No question there. So we're ready for step 5. If alpha is the bigger, then we reject the null hypothesis. What we're saying is the chances of getting this data with these averages for these sample sizes and even these standard deviations, the chances of that happening, if adults and teens actually got the same amount of sleep, the chances that our data would produce that information is this. I mean, way less than even 1%. We were saying the cutoff is 5%. The chances of us getting that data, if they really were the same between adults and teens, I mean, what is that? So there's 1%, a tenth, 100, like 6,000ths of a. This is just. It's much more likely that adults and teens just don't get the same number of sleep in the first place. So plenty of evidence here. We reject the null hypothesis. And if you wanted to know the interpretation, if you wanted it in a sentence, you might say there is enough evidence that teenagers sleep more than adults on average. You don't have to phrase it this way, but that works pretty well. Okay, let's stop this video here. In the next video, we're going to do another set of independent groups, and we're also going to look at the confidence interval. See you there.